Hi! In today's video, I'll be continuing on more operations on sets that we can do. In the previous video, I went through union, intersection, and complement. Feel free to look through it again. Today, we'll be going through an operation called the power set operation. It means you can form a set by collecting together all the subsets of A. And actually, the axioms in set theory define this to be a set. And so, this set, which is the set of all subsets of A, is known as the power set of A. We take an example to better understand it. So, if A is the set that contains the elements 1 and 2, well, we already know that the empty set is always a subset of A. We take the set 1, since the element 1 is in here, all the elements in here is an element in here, A, and so this is a subset. Similarly for the set that contains only 2, and of course A is a subset of A. And so the power set has 4 elements, namely the empty set, the set that contains 1, the set that contains 2, and the whole set. Look through the textbook again to better familiarize yourself with more subsets and what are the power sets of the original set. And in general, if A has finite elements, let's say they have n elements, then the power set will have 2 to the power n elements. You can look through my video on counting to see why. Now, more examples on the power set to make sure that you strengthen your understanding. If you have the empty set, there's no elements. So 2 to the power of 0 is 1. So the power set of it should be 1 element. And so it is the set that just contains the empty set. And we like to note that this does not equals to this, because this is 0 and this is 1 element. Now, if we take the power set of this new expression, it has 2 elements, the empty set and the whole set. And we do that again, we see that we get the empty set, the set that contains just the empty set, the set that contains the previous whole set, and the set itself. Just to take note and not be confused, just remember how many elements there are if it was the finite case. If it's infinite case, then you just need to be careful and familiarize yourself by practicing more. So, with this definition, let's do some proving. We have this proposition. A is a subset of B if and only if the power set of A is a subset of the power set of B. So, let's prove one direction first. We suppose this is true. We want to prove this is true. To show that this is true, we let an element in the power set of A, and now we want to show it's an element of the power set of B. To be an element of the power set of B, it means the element X must be a subset of B. And so, because we already know that X is an element of A, it's a subset of A, which then by transitivity, it's a subset of B as well. And so it's an element of power set of B, and hence we have proven one direction. Now we suppose the other way. In this case, we can use the fact that because A is in the element is an element of the power set, it will also be an element of the power set of B. And hence, A is a subset of B. Therefore, A is a subset of B if and only if the power set of A is a subset of the power set of B. I hope you have caught that. We'll move on, and you can rewatch the video again if you do not understand. Now, before we move on to the Cartesian product set, let's talk about something called ordered pairs. An ordered pair is always notationally x and y enclosed in round brackets. It is actually defined like this, and it has the property that x comma y equals to a comma b if and only if x equals to b and y equals to b. So you might ask, why is it defined like this? This is defined in this way to achieve this property. And so most of the time when we talk about ordered pairs, we are caring more about how we use them with this property of having the ordering matter, instead of caring more about this definition. And we can generalize that to an n tuple. So an n tuple just means you have n elements in a row, and if it equals to each other, it means each of these elements equal to each other. Now that you know how to use an ordered pair, we'll talk about this thing called the Cartesian product or direct product. So a Cartesian product of A cross B is just the set of all ordered pairs such that the first element is in A and the second element is in B. So an element in this product is just an ordered pair where x is in A and y is in B. You can expand this out in logic more clearly. And generally, you can do this for n number of sets, and then it will just be an n tuple. Taking a look at an example in the book, if your A is just K, L, and M, and B is Q and R, then the set of ordered pair is just K with R, L with R, M with R, K with Q, L with Q, and M with Q. But you can see that this does not equal to B cross A, because B cross A will have the first coordinate as R instead of the elements in A. So the first coordinate in B cross A will be B, and the second element will be in A, which is different from A cross B in general. A useful counting fact to note is that if A and B are finite, the number of elements will just be the number of elements in A multiplied with the number of elements in B. You can verify that yourself. And now, let's move on to a proposition. It deals with the empty set, where A cross the empty set is empty. Likewise for empty cross A. We shall prove this proposition, and since we already know the empty set is a subset of A cross empty, we just need to prove the other subset inclusion, which means that for all the elements in here is a subset of empty. But to be a subset of empty, it means that this is false. You want this to be false. And so, for this to be false, if you expand on the definition, if x is the element of this, it means that there exists an element in A and there exists an element in the empty such that this holds. But because there's no elements in the empty, this can't hold. And hence, x is an element of the empty, and so proven. Another proposition that we like to note is the distributive law of Cartesian product. Let's prove that A cross B union C is the same as A cross B union A cross C. Well, if we write out the definition, x is an element in this set if and only if there is an element in A or there is an element in B union C such that this holds. But this means that there is a set A and a set B such that A is an element of A, and when you expand on B union C, B is an element of B or B is an element of C, with X being the ordered pair. We have already proven in our tutorial in logic the distributive laws of n and all, and so we can expand out the logic law to form this. If we simplify them, it will be x is an element of A cross B or x is an element of A cross C. And so we can combine them together using union, which means x is an element of A cross B union A cross C. And these are all series of if and only if because they are from the definition. And hence we have proven our proposition. You can see how proving propositions in set theory lies fundamentally on the logic and your definitions. Let's do one more proposition to better understand the Cartesian product. So, in this case, what we want to prove is just a subset inclusion. You can imagine the diagram to be as follows. A union C is this big square, this big length, and B union D is this bigger length. And so when you cross them, you're like gathering all the elements in this big square. But A cross B will only give you the elements here, and union up the elements in C cross D is here. So these are the elements you're collecting. And so you can see it is within the bigger square here. And so it's a subset. And we can actually, there are counter examples to show why the other subset inclusion does not hold. So, to show that your element here means you want an element here to be an element here. It means you must be able to find elements in A union C and elements in B union D such that X is the ordered pair. Well, if you expand out the definition, it comes directly as follows. You already have an A, which is in A, or you have a C, which is in C. That means you can find an element in the union of them such that the ordered pairs is true. Because F will be in either B or D. And so you have proven the proposition just by expanding out the definition. You can see, many of times, set theory just comes down to the definition, and if you stick true with the logic, most of the propositions at our level is quite easily solved. Now, the next page in my notes has a counter example to this proposition for the reverse inclusion on why it doesn't hold. So feel free to download it and take a look after trying it out yourself. That's all for the video. I hope you have enjoyed it. And we're moving on to the last chapter in introductory intuitive sets theory in the next video. Thank you.